So good morning, everybody. Today we shall start a little bit of medical ultrasound, and we will not discuss in detail. Rather, we will just go through the key concepts and other things that are other technology that are used for medical ultrasound devices, and especially the phased array concept, and some basic concepts of imaging, image formation will be discussed. So instead of writing in a slide, I have taken the help of slides. These slides are taken from which are available. So basically, ultrasound medical imaging was as it is told here, it is started around 1940s, 1942, localizing brain tumor also. Before that, of course, ultrasound used to be used for monitoring stones, kidney stones, etc., but not as an image. 1950s image 2D grain scale images were displayed using ultrasound. 65 real-time imaging was also displayed. So that means that time that used to be analog video form, it is to be recorded. Compared to other imaging techniques like X-ray and MRI, MRI is magnetic resonance imaging, which is a very costly equipment. And X-ray is also, X-ray diagnostic is also very useful, but usually X-ray cannot be used for all purposes. And since ultrasounds have some distinct properties related to various or body organs, so therefore it can be used for imaging complementary informations. So these things we have already discussed, the ultrasonic waves and its properties. We have also discussed about transmission and reflections little bit in detail. Now here basically that I was talking during the beginning while we discussed about plane wave properties, that while tissue or human body is excited with ultrasound waves, because body mass texture is not very homogeneous. It has lot of inhomogeneities even within the organ itself. So therefore, the reflection that is coming out of the inside body is almost all the cases are specular in nature. So there is no regular reflection. So that way, acoustic scattering play an important role. So usually the scattering coefficients of various body substance are different. Means for various tissue regions, the scattering pattern is different. Generally, the imaging is taken in reflection mode, because in transmission mode, lot of acoustic energy will be dissipated and scattered through. It can be done in reflection mode profitably based on the discontinuities of the acoustic impedance. So like here is the transducer. If it is at a distance of d, so initially water bath used to be used. uh, for imaging. So that means if it is some hand is imaged or some part of the body is imaged, some water bath used to be kept around the body, and then the transducer used to be kept in that water bath. But now, of course, gel concept has come. So some gel is given at the skin surface, and then the transducer is scanned through the surface. So basically, the reflection comes from the differential acoustic impedance. So corresponding to the position of the transducer, one scan line will be created, and the subsequent echo will be echo amplitude will be recorded. And if we go to a different position, a similar one-dimensional pattern will come, and then from this multiple one-dimensional pattern, image formation can be made by some kind of registration process. So sound velocity that is given 1 by rho k, so that we have also discussed. Now we have discussed about the velocity of sound in generally metals, solids, liquids, or air. However, here you get the information of the body substance. Like for blood, the density is similar to water, very similar to water. And also the speed is very similar to water. The bone density is higher, so we have a mismatch, good acoustic impedance discontinuity between blood and bone. Similarly, brain is also similar to, very close to water. Fat is also close to water. Kidney is also close to water. Liver is close to water. Lung is porous, so therefore it is much less, 400. So then muscle is also quite close to water and all other things. So mostly the body density is close to water, around water, apart from lungs and bone. Bone density is of course higher. Similarly, the velocity is also like higher in bone, and others are basically very close to water. The velocity here for the lung, of course, it is, there would be a lot of reflections, but it would be average velocity could be between water, maybe less than water would be the velocity in lung. The muscle spleen, those velocities would be close to water only. So generally the acoustic waves, when it is scattered, it will go, unlike the plane wave, it will propagate in 3 dimensions. So if it propagates in 3 dimensions as a spherical wave, so then the phase will change in a radial fashion instead of a planar fashion like that we have discussed in our plane wave description, that the ultrasonic wave is some amplitude but into exponential of I into omega t minus kz. So basically that z is the distance of traveled. Now That equation, of course, is valid, but then at various directions, uh, the uh, propagations will be radially, unlike the plane wave. If it is a, if it we conceived that ultrasonic wave is generated from a secondary scatterer points inside the body. So therefore, that will be that will be given uh, by a displacement x, y, z, t. X, y, z are three-dimensional coordinates, and t is a time. So which can be, of course, can be simplified as longitudinal wave and transverse waves. So that also we had discussed that longitudinal waves are generated when vibration is lateral or longitudinal, and transverse wave is generally generated when the vibration is in shear mode. Now here the same thing, characteristic impedance is given for various body substances. As we can see, this is very important for imaging of human body, because generally the human body imaging is done by the reflections coming out of the various organs. So therefore, a sufficient discontinuity of acoustic impedance should be available. So blood to bone is a good acoustic discontinuity, and then we have had also relatively some discontinuity is available, but others like lung has a very good discontinuity. The others are very similar. Acoustic impedance is very similar. So therefore, for acoustic imaging, we have to see the variation of the reflection coefficients that are distributed throughout the organ, and generally, because they are very similar, it will be more or less homogeneous with some grainy pattern may come. But then if there is some foreign object inside trapped, maybe say in kidney stones are there. So in such cases that will be very prominent. Similarly, if there is say muscle and fat, there is a good discontinuity, that also can also be done. So here that wave equation that we have discussed about one-dimensional. So this is the wave equation that has been given here in 3 dimension, but the basic equation is same. That is del square z square p is equal to 1 by c square del square p del t square. So here it has been shown that from material 1 to material 2, how the wavelength is changing because of the change in velocity. For a certain frequency. Then reflection, transmission, that is explained, that we have already discussed. So for the plane wave, there can be total internal reflection as well at the interface. So as we were discussing that attenuation, scattering and absorption are the three fundamental quantities that are responsible to determine the contrast of a particular point when ultrasound imaging is being done. So this also we have discussed attenuation coefficient, amplitude attenuation coefficient and energy attenuation coefficient, that this also we have discussed. Now the attenuation coefficient of ultrasound waves, those are given in various organs and materials inside the human body here. So like fat, this is in dB per centimeter per megahertz. So for fat it is 0.63, then muscle fiber 1.3, along the fiber, that is along the length of the fiber. When it is across the fiber, attenuation is more because a lot of discontinuities will come from fiber to fiber. Cardiac muscle is 1.8, blood is quite less, 0.18. Bone is quite high, 20.
সবগুলোতেই ঠিক করতে হবে না? Sorry.
So this small a is given as a normalized in terms of frequency. So that as we can see, lot of discontinuities are there in lung because of air trapped in alveoli. So their attenuation is the highest. Bone is also is porous, and there is a lot of trapping minerals in bone, so that also gives rise to high attenuation. Similarly, in the brain, we can see that there is differential attenuation between white matter and grey matter. So therefore, that also can be differentiated. However, attenuation reconstruction, profile reconstruction is not as easy as as detecting the reflection, that is acoustic impedance discontinuities. So the amount of attenuation would be depend the depth of penetration and the time of propagation. So therefore, depending on the time of propagation, so we can have a time gain compensation for the imaging purpose and getting a good contrast with varied penetration depth. So the gains need to be compensated. So we have discussed about piezoelectric crystal. So here, of course, some construction is given here. Plastic cable, acoustic insulator, that is backing the absorbing medium for sound. Then the crystal, and then insulated cover and matching medium is at this place. So when so there are another important thing that we have to discuss, that when we model the ultrasound generation as a point source, then of course it will go in 3D as a spherical wave. However, because this source has a dimension much greater than the wavelength of the ultrasound, if we excite at a particular frequency of, say, some megahertz, then the wavelength will be in micrometers. So therefore, of course, it depends on the velocity. So, but the size of this uh, ultrasonic probe is much higher than the wavelength. So in such cases, actually the front end of the source need to be modeled as multiple point sources. Had it been a point source, then from like this, there would be diverging beam patterns in a cone, it will go. Now, if we have a multiple a source which is a combination of multiple point source, so therefore all such point source will radiate in divergent fashions, like the planes. So basically, due to various diverging patterns, a combinations there will be phase interfer due to the differential phase. There will be constructive and destructive interference will be created at each place, and finally we will have an average energy distribution patterns. So if this d square by lambda is much less than 1. Generally, that zone is known as the near field zone, and if Z is much greater than d square by lambda, lambda is the wavelength, d is the dimensions of the source. So then that is known as the far field pattern. So the far field pattern is usually can be approximated as if it is coming from a point source with an aperture. Okay. So had it been a perfectly point source, then in all direction the radiation used to be there. But because there is a distribution of point sources, so there will be an aperture that will come into picture. So in between this zone is known as the Fresnel zone, and the other zone is known as the Fraunhofer zone. So in between Fresnel and Fraunhofer zone, the near is the near field zone and this is the far field zone. So here we have a depth of focusing zone. So this is the depth of focus zone. So as I was discussing for approximate field pattern, if a focus transducer can be thought like this from a plane aperture. Now, while collecting the echo, the reverse, that was source modeling, source pattern, radiation pattern modeling. The same thing will be replicated when we are collecting uh, the sound energy at the transducers. So these are basically the distributions either for array of transducers, which can be thought of array of point sources, and then finally their collective patterns will be in the same fashion, just the pattern that it has followed for radiation. So therefore, the returning echoes will correspond to a delay uh, corresponding to the path that it has gone. Now, if we assume to be more or less a point pattern and a circular wave, so this wave front of the delayed echoes, returning echoes will be more or less circular. And corresponding to that, actually, we can have a delay given in the circuit. Some electronic delay can be created in the circuit uh, to uh, to measure or to address the depth, same depth at various orientation. Because the delays are different at different directions, so some compensation has to be done. So that is done by this block, which is here shown as the digital dynamic focusing. And then finally, it will be shown as a time versus depth. This kind of echoes will come. Now, generally, as we have seen that near the resonance, what will happen? There will be oscillations. All circuits near the resonance oscillates, and because ultrasound probes for medical imaging are operated near that resonant region only for achieving high efficiency, so there will be ringing artifacts or resonant artifacts will be there. So given a pulse, the resultant output of sound waves will be like this. And similarly, the echoes will be formed as the time progresses with an attenuate and versus of the original launched pulse. So this is one example of a transducers that we had discussed earlier also. Now, this pulse wavefront management or energy distribution management can be done by appropriately introducing a delays corresponding to various position of the transducer, either for receiving purpose or for transmission purpose. So this for both receiving or transmitting, if we introduce the delay, basically we will be addressing energy corresponding to a certain direction. Say while transmitting, if we excite this array of piezoelectric transducers at a like a pattern, linear delay pattern, then what will happen? The beam front will be deviated. The beam front will be deviated because because of the delay, this one has been excited quite late, so it has propagated only this much of distance. Similarly, this wavefront is propagated into this much and like that. So we have a linear wavefront, almost linear wavefront is created, and the normal to this linear wavefront, or if we draw the normal to this tangent, then that will give us the beam energy direction or the overall beam energy direction. So as you can see, by that we can steer the beam at a particular directions by varying the delay amount. So by varying the delay amount or the slope of this delayed amount, so we can steer the beam at various angle. The focusing is done again, can be done by varying the delay in this manner, that the two endpoints have minimum delay and the midpoints has the maximum delay. So that way, uh, this is reaching here at a delayed time. And if we now draw the tangent, so that will be a curvilinear one, and the net energy beam will be, if we draw normals at multiple points, then uh, this will be focused to a point. So depending on here also, by varying the delay, we can uh, increase or decrease the focal length. So here are some pictures of the transducer arrays are given. So generally, as we have seen that we have these approximations of this approximation. This approximation is not, just linear or parabolic, but there are a lot of fluctuations in between in the profile. So now, if we want to know the energy distribution, we have to take the Fourier transform of this aperture. Now, if we take the Fourier transform of this aperture with this detailed informations of these wave fronts, then what will happen? There will be one main lobe and lot of side lobes will come. So that side lobes generally come due to the finite aperture of uh, the radiator. Had it been a perfectly point source, then pure uh, spherical wave pattern used to be there. But because it is not a perfectly point source, so with respect to lambda, so therefore even that individual sources are not a point source. The dimensions of piezoelectric crystal uh, to couple sufficient amount of energy that are quite large. So therefore there will be a beam radiation profile will come, and a typical beam radiation profile is shown here. This is the main lobe radiation profile, and there are two side lobes. Now there are several ways imaging can be made. The simplest kind is that we put a transducer at a particular position, then launch a pulse, and then monitor the amplitude of the reflection pulses. So wherever the reflection is more, so we can see that one as the major discontinuity of the acoustic impedances. So this is known as the amplitude A mode. So that means the reflected pulse is plotted with respect to time, and if we know the velocity, this time axis can be also converted to the depth axis. So assuming that the velocity more or less same, or maybe at a different medium, if we can compensate the velocity difference, that way we can have the better depth information. So then this can be coded in terms of depth. So once we know the depth information, so this depth information uh, uh, will correspond to the particular transducer position. Now the transducer position we can shift at laterally or in the transverse manner to get another amplitude profile like this. So along each line we transmit a pulse and plot the reflections that come back versus time. As a body, human body and its organ are quite complex in terms of scattering points and its distribution. So therefore, generally, it's not very easy to correlate these amplitude patterns unless it is put in some context. Now, in the imaging mode, uh, that that is that this is the amplitude mode where reflections are being made. In the imaging mode, what is done that the gray level intensity of is coded with the amplitude, and subsequently the position is an XY scan is used to have a position. So like that here multiple depths are being scanned. M stands for motion. This is motion mode display. One is A mode is amplitude mode, B mode is brightness, as the pixel brightness is basically uh, proportional to the reflection component. Motion mode is basically the echoes are traced from a moving organ, like due to breathing or some other movement of the organ, there will be some, the reflection points will move. Now, uh, if we correlate those reflection points with time, then we can have uh, a mode image generated. So A mode is very difficult because of a lot of scattering point is there. So if we plot them discretely, like these reflections are coming at a certain time, and then for different scans, it will be very difficult to interpret. So the imaging is done usually digitally by steering the beam at a certain angle and then monitoring the corresponding echoes. And then the depth time profile is converted to the depth profile, and we have the intensities available at a polar coordinate, rho theta coordinate. The rho theta coordinate can be transformed to XY coordinate by doing suitable transforms. Of course, from the rho theta also we can reconstruct the image and uh, can find out various transforms in rho theta as well. Usually rho theta transformations are done mathematically represented what is known by that radon transform. So like when we are when a certain beam is propagated in these directions, the total attenuations will be given by the sum of all attenuations along this beam. Okay. Similarly, all such orientations will be there. All such orientations will be there. Now, if we have multiple measurement, then what will happen? The same point will be contributed to different point intensities. From one point, I have the sum of all these intensities. I move this point, again take another orientations. The same number of pixels are contributing as a sum of image to another uh, output. So all such output then can be iteratively reconstructed through some method which is known as back projection principle used in X-ray tomography. For ultrasound tomography also that can be used. However, because ultrasound we have another information that is time, which is very useful. And so that's why if we quote the time, more or less the depth information is known. So using these two together, we can have a better imaging. So that means using tomography principle also we can reconstruct back certain amount of information, and then by depth coding with respect to time also we will get certain amount of information. So using these two we can do better reconstruction. Whereas for X-ray tomography, of course, we cannot do the depth coding in terms of time because the velocity of electromagnetic wave is quite high. So therefore, the resolution in time required for depth coding is very low, so which is extremely difficult. So they are mostly those transform-based and projection-based reconstruction are used. However, ultrasound, the most imaging procedures use this uh, depth time coding. So this has been shown here. So corresponding to various line, along this line the reconstruction will be made. So the pixel values will be set in a rho theta coordinate. And then we can convert to the rectangular coordinate here, wherever necessary. So that's why ultrasound images are displayed in a conical form, because the basic coding is done in the rho theta coordinate. This is one block diagram which has been shown here. Time gain compensation. Then beamformer is basically to program the time delays, appropriate time delay. Scan converter is the converting that depth information and the XY information together. Then there can be some post-processing that I was talking of for reconstruction. There is some example is given. So like for external imaging, each line corresponds to like 20 centimeter depending on the transducer threshold, detection threshold. we can give that depth here. And velocity of sound is 1540 per millisecond. Travel distance from and to transducer will be 40 centimeter if depth is 20. Then acquisition of line takes around 260 microsecond. Typical image has 120 lines for total time of 31 millisecond. So image is reconstructed therefore almost in real time. So because it is 31 millisecond, so we can have maybe images at 30 hertz. Now, of course, scanners are available with much higher scanning rate. So there are multiple scan lines simultaneously can be scanned. So instead of one probe is scanning throughout, multiple probes can be scanned simultaneously. So here is another example is given that cardiac image is here, but as you can see, this is not that clear like MRI or X-ray because ultrasound wavelength is comparatively much larger with respect to electromagnetic waves. Those are used. MRI, of course, used a different principle, but it has also good resolution in millimeters. Whereas X-ray can have resolution fraction of millimeters, depending on the doses possible. Ultrasound has 1-2 millimeters kind of maximum resolution. So another example is shown here. Now, another thing that we can talk that if we incorporate the frequency shifting information of the sound embedded into the measurement, then basically we can know the movement of the various organs or substances like blood. So therefore blood flow and blood flow patterns can be monitored if we could code this imaging informations with frequency shift as well. So there are various kind of Doppler principles. Those are used for ultrasound. The continuous wave Doppler, which is that one crystal is excited by a sinusoidal wave and then the frequency shifts are monitored. We can have a pulsed wave Doppler based on pulse repetition frequency. Then there are color flow Dopplers are also there. So where basically the velocity component is registered along with the temporal scan coding, and then corresponding to a theta line, the location of that velocity component can be put. Here it is shown that there are some zones where red coated flow directions are uh, also measured. If we want to measure the flow direction, as I had discussed, that we have to have some DC shift given to the Doppler, then we can measure the flow directions. So that way here it has been shown the mapping of the flow along with direction. So for 3D, this principle can be elaborated further, and the scanning can be made not only in XY but in XYZ. So that way 3D scan is also possible. So there are many applications of ultrasound, especially for applications where X-ray is not that much safe or used for neonatal cases and also for maternal applications. Here is an example for brain scan is also given, where basically intraventricular hemorrhage has been located. I think this is like we have just gone through like a storytelling. Maybe we shall discuss a little bit of the detail of these things in a